Hi, I'm Dr. Shanice O'Mara and I hear you want to learn physics. I have to say, good choice. Physics is the science of how the world, really the whole universe, works. And I don't know if you've noticed, but the world I live in, things tend to move around a lot. So that's what we're going to study first, the science of motion. And it turns out to be incredibly useful for figuring out things like where you are, where you've been, or how you're moving through the world. Why is that worth knowing? Well, for one thing, the police use physics to decide exactly how fast you're moving through the world, and if that motion happens to break the law. So if you're going to understand how and why you got that ticket they gave you, and maybe even know enough to dispute it, you have to know the science of motion too. And in order to do that, you'll need to understand a few essential conditions that describe your physical place in the universe. Conditions like time, position, velocity, and acceleration. So to talk about all of these things at the same time, you'll need a set of equations that links all of them together. These are called the kinematic equations. So for the next few minutes, let's talk about how you can figure out your place in the world, literally, which just might help you beat that speeding ticket. Let's say you're driving on a straight stretch of highway, say someplace nice and flat, on the wide open spaces of the northern plains of the United States, say North Dakota. You come across a red light, and even though there are no cars in sight, you stop, because you're a good driver who obeys traffic laws. Then the light turns green, so you hit the gas, and exactly 7 seconds later, you hear the sirens and see the flashing lights of a police car. You're promptly served with a ticket for speeding in a 100km/h zone. But wait, were you really going that fast? Did you actually break the law? You can't really tell because the speedometer in your car is broken. So you need to find another way to figure out how fast you were going and decide if you want to take this up with Johnny Law in court. That's where physics comes in. The physics of moving in a straight line. Let's start by talking about how your car was moving. Driving along a straight highway is an example of one-dimensional motion because the car can only move back and forth along that line. That's the difference from something that's free to move in all 3 dimensions, like a boomerang flying through the air. And instead of describing that motion just in terms of speed or direction like a police officer or other non-physicists might do, we physicists describe it with math. Maths that measures the 4 main conditions of the car's movement. It's time, position, velocity, and acceleration. Time simply tells you how long you were driving for. Position is also important. It lets you know where you are and where you were. It can even be negative. For one-dimensional motion, there are only 2 directions you can move in. In this case, forward or backward, east or west. So if the change in position, known as displacement, is positive, you'll know you've moved in one of those directions. If it's negative, you're travelling the other way. But which direction is positive and which is negative? That's totally arbitrary. You could decide that east should be positive and west negative, or the other way round, but the answers you get will mean the same thing. You just have to make sure to keep track of which direction is positive and keep that in mind when you're talking about velocity and acceleration too. Velocity is the way your position changes over time, and it's also a pretty big deal. It's kind of like speed, but just like with displacement, it also tells you which direction you're moving in based on whether it's positive or negative. Now, what about when your velocity changes? That's the 4th quality of movement you'll want to pay attention to. Acceleration. If you've ever been in a car when someone slammed on the gas, that feeling of being pressed back against your seat is acceleration. Your velocity is changing. So how do we plot out all of these different conditions that describe the movement of you and your vehicle through the plains of North Dakota? A non-physicist might visualize this movement on something like a map, but for us, graphs are the most useful way to show how all this change in position is happening. Graphs are generally presented as position versus time, with position on the vertical axis and time on the horizontal axis. We'll label your position as X and time as T. Now let's imagine 3 different scenarios for how you drove through this small town and graph each one. First, let's say that after you went through the red light, you just stayed in one spot, say at 4 meters from the light, for 3 seconds. From that moment, the graph of your position would just be a flat line at x equals 4 meters, like this. Now what if you didn't stop, but instead were coasting at 1 meter per second? Then the line would be diagonal to show how your position was changing, like this. And the third time, let's say you were standing still at first at the 4 meter mark, but then you hit the gas. and you moved in such a way that after 1 second you went 1 meter in the positive direction, and after 2 seconds you went 4 meters, and after 3 seconds you've gone 9 meters. In that case, you end up with a graph that's all curvy like this. But there's more going on in these scenarios than just your position and time. You also have to be able to graph your velocity and acceleration. So to graph your velocity, you'd put your velocity on the vertical axis and time on the horizontal axis. And you'll note, since velocity is measured as the change in position over time, it's measured in meters per second. The graph for acceleration is quite similar. Acceleration, A, goes on the vertical and time goes on the horizontal. And since acceleration is measured as the change in meters per second, its units are meters per second, otherwise known as meters per second squared. So time, position, velocity and acceleration all relate to each other. Velocity is the change in position over time, and acceleration is the change in velocity over time. And often, your velocity will be different from moment to moment, like the third time you drove down the highway when you hit the gas. But let's say you wanted to know your average velocity for a certain period, say for those first 3 seconds. All you have to do is take the change in position and divide it by the change in time. Figuring out how much something is changing just means that you have to subtract its starting value from its final value. Since, as physicists will end up doing that a lot, we abbreviate that difference using the lowercase Greek letter delta. So we can use that to write the equation for average velocity. It's just delta x over delta t, the change in position over the change in time. Now what about the third scenario, when you had your foot on the gas and kept accelerating? You started out at the 4 meter mark and ended up at the 13 meter mark. So your change in position, or delta x, would be 13 minus 4, or 9 meters. You started at 0 seconds and ended at 3 seconds, meaning that your delta t was 3 seconds. Over 3 seconds, you moved 9 meters. That's 3 meters per second. The equation we use to describe average acceleration is a lot like the one for average velocity, because it's just the change in velocity divided by the change in time. So in that case, your equation would be delta v over delta t.
Topic: balanced and unbalanced forces. How are we able to stand on the Earth without falling into the center of the Earth? Don't know the answer? No worries. We shall find the solution.
Oh.
Aha!
Oh yeah! Huh?
Hey, that was a nice balancing act. Do you know there are certain forces around us which keep us balanced or unbalanced? Force is a push or a pull exerted on an object. Every object on the Earth experiences various forces. When a number of forces acting on an object are such that their resultant force is 0, then the forces are said to be balanced. Whereas when a number of forces acting on an object are such that the resultant force is not equal to 0, then the forces are said to be unbalanced. When he was falling, which forces were acting on him? Were they balanced or unbalanced? In this case, unbalanced forces were acting on him. On Earth, many forces act on an object. One of them is gravitational force of the Earth. Gravitational force of the Earth is the force which pulls all the objects downwards, that is, towards the center of the Earth. Let's get back to the question. When he was falling, the gravitational force overpowered all other forces. So, the resultant force was not equal to 0, and hence, we can conclude that unbalanced forces were acting on him. Did you see that? He landed safely. But if the gravitational force was pulling him towards the center of the Earth, why did he fall on the ground and not into the center of the Earth? We know that gravitational force is pulling us downwards. However, there is another force exerted by the ground which pushes us upwards. This force is called the normal force. It is equal to the gravitational force. Normal force is exerted by a surface only when we are in contact with it. Since these two forces acting on us are equal but opposite to each other, their resultant, that is, net force, is 0. Thus, these balanced forces keep us from falling into the center of the Earth.
A force is a push or a pull. A force of some kind is always required to change the state of motion of an object. The combination of all forces acting on an object is called the net force. The net force on an object changes its motion. The net force depends on the magnitudes and directions of the applied forces. When two forces are in the same direction, their magnitudes are added and the direction of the net force is in the same direction of the two forces. When the forces are in opposite directions, the two magnitudes are subtracted and the net force is in the direction of the larger of the two forces. If the two forces are opposite in direction and equal in magnitude, the net force is zero. When the girl holds a rock with as much force upward as gravity pulls downward, the net force on the rock is zero. A stretched spring is under a stretching force called tension. The upward tension in the string has the same magnitude as the weight of the bag, so the net force on the bag is zero. The bag of sugar is attracted to Earth with a gravitational force of 2 pounds, or 9 newtons. There are two forces acting on the bag of sugar, the tension force acting upward and the weight acting downward. The two forces on the bag are equal and opposite. The net force on the bag is zero, so it remains at rest. Mechanical equilibrium is a state where no change in motion occurs. Whenever the net force on an object is zero, the object is in mechanical equilibrium. This is known as the equilibrium rule. The sigma symbol stands for the sum of. The capital F stands for forces. For a suspended object at rest, the forces acting upward on the object must be balanced by other forces acting downward. The vector sum equals zero. The sum of the upward vectors equals the sum of the downward vectors. The sum of the forces equals zero, and the scaffold is in equilibrium. What forces act on a book lying at rest on a table? One is the force due to gravity, the weight of the book. There must be another force acting on it to produce a net force of zero, an upward force opposite to the force of gravity. The upward force that balances the weight of an object on a surface is called the support force. A support force is often called the normal force. The table pushes up on the book with as much force as the downward weight of the book. The two forces add mathematically to zero. The state of rest is only one form of equilibrium. An object moving at constant speed in a straight line path is also in a state of equilibrium. Once in motion, if there's no net force to change the state of motion, it's in equilibrium. An object under the influence of only one force can't ever be in equilibrium. Only when there's no force at all, or when two or more forces combine to zero, can an object be in equilibrium. When the push on the desk is the same as the force of friction between the desk and the floor, the net force is zero and the desk slides at a constant speed. If the desk moves steadily at a constant speed without change in its motion, it's in equilibrium. In this case, the sum of the forces equals zero means that the force of friction is equal in magnitude and opposite in direction to the pushing force. The tension in the rope is 300 newtons, equal to Nellie's weight. The tension in each rope is now 150 newtons, half of Nellie's weight. In each case, the sum of the forces is equal to zero. To find the resultant of non-parallel vectors, we use the parallelogram rule. Consider two vectors at right angles to each other. The constructed parallelogram in this special case is a rectangle. The diagonal is the resultant R. When Nellie is suspended from rest from the two non-vertical ropes, is the rope tension greater or less than the tension in the two vertical ropes? You need to use the parallelogram rule to determine the tension. Notice how the tension vectors form a parallelogram in which the resultant R is vertical. Nellie's weight is shown by the downward vertical vector. An equal and opposite vector is needed for equilibrium, shown by the dashed vector. Notice that the dash vector is the diagonal of the parallelogram defined by the dotted lines. Using the parallelogram rule, we find that the tension in each rope is more than half her weight. As the angle between the ropes increases, tension increases so that the resultant remains at 300 newtons upward, which is required to support Nellie's 300 newton weight. When the ropes supporting Nellie are at different angles to the vertical, The tensions in the two ropes are unequal. By the parallelogram rule, we see that the right rope bears most of the load and has the greater tension. You can safely hang from a clothesline hanging vertically, but you'll break the clothesline if it's strung horizontally. Copernicus announced the idea of a moving Earth in the 16th century. One of the arguments against a moving Earth was this. Consider a bird sitting at rest at the top of a tall tree. The bird sees a worm, drops down vertically, and catches it. It was argued that this wouldn't be possible if Earth moved as Copernicus suggested. The fact that birds do catch worms from high tree branches seemed to be clear evidence that the Earth must be at rest. You can refute this argument using the idea of inertia. Earth moves at 300 kilometers per second, but so do the tree, the worm below, and even the air in between. Objects on Earth move with the Earth as the Earth moves around the Sun. Earth doesn't need to be at rest for the bird to catch the worm. If we flip a coin in a high-speed car, bus, or plane, we can catch the vertically moving coin as we would if the vehicle were at rest. We see evidence for the law of inertia when the horizontal motion of the coin before, during, and after the catch is the same. The vertical force of gravity affects only the vertical motion of the coin. Flip a coin in an airplane, and it behaves as if the plane were at rest. The coin keeps up with you. That's inertia in action.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most defensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
We're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you're coming in and making a tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and/or speed.
So imagine that a quarterback is just taking a snap from the center, and a lineman gets free from the opposing team and is coming from the other side. And when they collide, you can see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics, a player's natural resistance to that unbalanced force is something called inertia.
On the football field, you can think about inertia as being a running back who's already in motion doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make him hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass is different from his weight. Mass is a measure of how much matter an object has, while weight is a measure of how strongly an object's mass is attracted by gravity.
So for example, a body on Earth would have the same mass as that body on the moon, but it would weigh less on the moon because gravity is less on the moon than it is on Earth.
NFL players with more mass have more inertia and are harder to move off their path. This concept even works on a quarterback sneak, when a quarterback uses the combined mass of his entire offensive line to gain a yard or two.
If you've got an offensive line that can overpower the defensive line, that's just what you do. You get on their hip and you just fall, and you just ride that wave forward.
In the NFL, whenever players go head-to-head, it's Newton's first law of motion that helps determine who will win the battle of the gridiron. To be an NFL kicker takes more than just nerves of steel and a strong leg. It also requires help from one of the key laws of physics.
It's easy to say, well, I just kicked the ball. Well, let's delve into it. Let's look at the specifics. What actually happens when you kick the ball, and why does the ball go where you ask it to go? And it is Newton's second law of motion.
The second law is one of 3 laws described in 1687 by Sir Isaac Newton, who used them to describe how and why objects move.
So the second law says if you have an object with a mass that is accelerating, and acceleration means a change in velocity, that is equal to the amount of force applied to the object. The way we say it with words is F is equal ma.
This also means that in order for an object like a football to accelerate, a force must be applied. To illustrate Newton's second law in kicking, we asked Morton Anderson, the NFL's all-time scoring leader, to perform his craft in front of a high-speed phantom camera. The entire procedure unfolds in less than a second and a half, from snap to hold to kick.
It's all about training and rehearsing and doing something over and over and over again.
To reduce the chance of a block, NFL kickers take just 3 steps to the ball. The final step is with the plant foot, which provides the stable platform for the kick.
I call it the moment of truth, and the moment of truth is basically when your plant foot hits the ground next to the ball. You're either in the right position or the wrong position.
The kick itself involves the entire leg building the force necessary to launch the football.
It's a hammer, and you're swinging the hammer, and you're trusting it, and it's going to be, impacting the ball with great velocity.
An NFL kicker's foot is in contact with the ball for just 8/1000ths of a second, and in that time, his foot applies up to a ton of force to the ball. This quick, violent strike is a perfect example of what's known in physics as an impulse.
Impulse is an important concept because there is a finite time over which the foot is in contact with the ball, and during that time there's a force applied to the football.
An impulse is equal to the force multiplied by the time the force is applied, represented by delta T. If force is graphed versus time, it's possible to see how a larger force or a longer time for the force supplies a bigger impulse.
Since impulse is really just the change in momentum, and since a ball doesn't change its mass, we're really just talking about the change in the speed. The bigger the impulse, the bigger the change in speed, which means the faster the ball is moving after it leaves the kicker's foot.
Ironically, Anderson says the distance of the field goal doesn't change his approach to the kick itself.
Mentally, you want to look at a 50-plus yarder, like a 40-some yarder, with some room to spare. I think that's a good way to kind of fool yourself into thinking it's a shorter kick.
Whether the kick is short or long, Newton's second law explains what an NFL kicker must do to send a football through the uprights. Whether it's a lineman stuffing a running back or a safety colliding with a wide receiver, all NFL defenders have a single-minded goal: to stop the ball carrier.
The object of making a tackle is you want to get the guy down and limit the amount of yards he's able to gain, especially after contact.
When a tackle is performed correctly, it's not just a thing of defensive beauty. It's also an elegant depiction of Newton's third law of motion, sometimes called the action-reaction law.
Newton's third law says that each action or force has an equal and opposite reaction. So if I were to push against the body, that body is going to push back against me with an equal and opposite force.
An important part of Newton's third law is the concept of momentum, which in football is the mass of a player multiplied by his velocity, represented by the formula P equals mv. NFL players may not know the formula, but they're keenly aware of the role momentum plays in tackling.
It's very important to have some speed and momentum as you're going in to make that tackle. The better you're able to use that to your advantage, the better you're able to make contact and get a guy down right away.
In every collision on the football field, Newton's third law dictates that the total momentum between players must be the same before the collision as it is after the collision. This relationship is referred to as conservation of momentum.
The law of conservation momentum says that the P, the momentum before the collision, is equal to P, the momentum after the collision.
This law, represented by the formula P before equals P after, can be illustrated with a simple toy called a Newton's cradle.
In this case, we have displaced an initial sphere, and when we let it go, it has some momentum. It's mass times velocity. When it impacts the next sphere, that momentum is transferred through the middle three spheres and then passed on to the final sphere. And so because it has the same mass, it will move away with the same velocity that the first sphere impacted the middle three spheres.
The interaction of balls on a Newton's cradle can help illustrate what's known as an elastic collision, defined as one in which there is no loss of kinetic energy in the form of heat, sound waves, or deformation of the object. On the football field, collisions are typically inelastic collisions because kinetic energy is released, mostly in the form of compression between the players' bodies and sound waves.
Inelastic collisions are the rule of the day. We see them all the time in football. That is, the energy of motion of two runners. After they collide, that energy is dissipated in deforming their bodies. That's like a spring. So some of your energy of motion went into that compression. You might have heard a loud snap from our pads. Some of the energy of our collision was transferred to the energy in the air that you hear.
While big hits look and sound spectacular, what's most important in tackling is stopping the ball carrier's forward progress.
If your pads are underneath his and you're hitting on an upward slope, you direct the energy up and you take him back. At the point of contact, hopefully that's where the ball stops play in.
Whether a tackle is successful or not, we can be certain that the same force is exerted on both players, and the total momentum before and after the collision is the same. For that, we have Newton's third law to thank.